Here we have two examples of how to use the binomial probability distribution to calculate probabilities. The first one is we're going to be looking at some census data. It says 8% of the population in the United States has earned a master's degree, and we're going to randomly select 10 people. And the first question is, what is the probability that exactly one of them have a master's degree? Okay, so the first thing I want to do is kind of go through the problem and pick out some numbers we might need. So we have 8% of the population has earned a master's degree. We have 10 people, and we're looking for the probability of exactly one of them. And in binomial distribution problems, you're always looking for n, p, and x. So n is going to be our number of trials, or our total number of people that we've selected. The probability that any one of them has a master's degree is 8%. I'm going to change that to a decimal for 0.08. And in our question, we want the probability that exactly one of them has a master's degree. So x, our number of successes, is going to be 1. If we need q, let's just calculate it now so it's out of the way. Q is 1 minus p. 1 minus 0.08, and that would give us 0.92. So we should have everything we need now to plug into the binomial equation here. So I'm going to start filling that out. X is 1, so the probability of 1 person out of 10. N is 10, so 10 factorial divided by 10 minus 1 factorial times 1 factorial. P is 0.08, and that's to the x, which is 1. Q is 0.92, and that's to the 10 minus 1 power. Alright, so let's bring up our calculator and see how to put this in here. Alright, so first number is 10, and factorial, again, that's in our math section. Arrow over to probability, and you can see it's number 4, factorial. And I'm just going to solve this, and we'll start writing down some numbers. So that's 10 factorial. On the bottom we have 10 minus 1 factorial, which would be 9 factorial. So let's get that one on here. Okay. Put that where it belongs here. 1 factorial is just going to be 1, so we can leave that there. Okay, now we need 0.08 to the 1 power. Anything to the 1 power is just that number. And then we need 0.92 to the 9th. So 0.92. If you need something bigger than squared on these calculators, use the little hat symbol, which is right here under clear, and go to the power that you need. So we went to the 9th power, and hit enter. So we have 0.472, round to 3 decimal places. Alright, so now if you take a look at our equation with the numbers in it, the top number is 10 times as big as the bottom number here. So if we divided that out, we'd end up with 10 times 0.08 times 0.472. And we're still looking at the probability of 1. Let's keep that on here. So let's multiply that. So we need 10 times 0.08 times 0.472, and we get 0.3776. And that's our answer. That is the probability that if you select 10 people randomly from the US population, exactly one of them would have a master's degree, is just under 40%. So a quicker way to do these problems without using the binomial probability formula is to just have your calculator do it automatically. So I have the binomial PDF function, and it's going to be n, p, and x. So n is 10, p is 0.08, and x is 1. And we're going to do this under the distribution menu. So I'm going to hit second vars for distribution, and we're looking for binomial PDF. Oh, there it was. So we enter n, 10, comma, p is 0.08, comma, x is 1, hit enter, and there's our answer, 0.3777. And if we compare that answer that our calculator gave us to the answer we got earlier, 0.3776, they're very close. So that is when x is just a single number. Alright, next one. What is the probability that at least one has a master's degree? At least one would be 1, 2, 3, all the way up to all 10 of them. So we could do this equation that we just used over and over again. We could do it for x equals 1, x equals 2, x equals 3, all the way to x equals 10. That sounds like a lot of work. So we need to remember our complement rule. So the probability of at least one is the complement of 0. So the probability of none. If we can calculate just the probability of 0 and subtract that from 1, then we'll have the probability of at least 1, or 1 or more. Right. So let's do our numbers over here again. N still is 10, P is still 0.08, X now we're going to use 0, and then remember that's the complement, and Q is still 0.92. So the probability of 0 is going to be 10 factorial divided by 10 minus 0 factorial times 0 factorial. And P is 0.08. X is 0. 0.92 to the 10 minus 0. Now, if you look at what we're going to end up with here, 10 factorial divided by 10 factorial, because 10 minus 0 is 10. 0 factorial by definition equals 1. So I'm just going to put that over here so you remember that. 0 factorial equals 1. So when you take this whole first part of the equation, you're just going to end up with 1. Because you have 10 factorial divided by 10 factorial. Anything to the 0 power, also by definition, is 1. So we have 1 times 1. And then we're going to have 0.92 to the 10th. So one quick calculation, that's all we need. 0.92, and then use our little hat button to the 10th, and we get 0.434. But then remember this is the probability of 0, and we wanted the probability of at least 1, so we need the complement. So we subtract that from 1, and we get 0.566. So again, a quicker way, let's try it with the calculator function, binomial PDF. N is 10, P is 0.08, X is 0. Again, we're calculating the complement. So second vars for distribution, binomial PDF, N is 10, P is 0.08, and X is 0. We get 0.434. And that's the probability of 0, and we want the complement of that. And there. Those two numbers, again, are the same, or they'd be very close if they weren't exactly the same. So the last question then, is it unusual to randomly select 10 people from the US population and find that at least one of them has earned a master's degree? Since the probability of at least one of them having a master's degree is 56.6%, 0.566, we would say no, that's not unusual at all. Typically a cutoff of probability for something being unusual, we'd use 0.05. Sometimes it's 0.01, sometimes it's 0.001. It really depends on the problem. So make sure you check every problem, and if they give you a cutoff value to use that in making your decision. So let's scroll down to the second example. This one has to do with a slot machine. The probability of winning the jackpot is 1 out of 2,500. And we want to know what's the probability of winning the jackpot one time if you play 10 times. So again, let's summarize our numbers. So we have a probability of success is 1 out of 2,500, so that's going to be P. And let's convert that to a decimal right away because that's easier to work with. We have N. If you play 10 times, you'd have 10 trials. And we want to know what's the probability of winning the jackpot one time. So X is going to be 1. Okay, so I'm not going to use the binomial formula anymore. We're just going to use the calculator. So N is 10, P is 0.0004, and X is 1. Let's clear that. So distributions, binomial PDF, 10 times, 0.004 for P, win one time. The probability of winning one time if you play 10 times is 0.004. We'll round up. Okay, so not a very good probability. You would think though if you played 2,500 times that you would win one time, but the probability of winning one time out of 10 tries is much, much smaller. So we have a claim here for the second one that someone won the jackpot twice in 10 tries on the same slot machine. And we want to know what's the probability of that actually happening. So again, we have P is 0.0004, N is claimed that they played only 10 times and won twice, so now X is going to be 2. And we'll plug that in. And do a quick calculation. So here we have 7.17, and then if you look over to the right, it says E minus 6. That means it's 7.177 times 10 to the negative 6th power. And I'm just going to round that. I'll just say 7.18 times 10 to the negative 6th, which is the same as this very small number, or you could report it as less than 0.0001. So, does the guess's claim seem valid? No, that's a tiny, tiny probability. It's not impossible, but it's very unlikely.